Hi guys, our very main topic is about nomenclature, and I'm going to tell you what is nomenclature. Nomenclature is the naming of chemical compounds. Nomenclature is a set of rules to produce a systematic name for chemical compounds. Wait, what is chemical formula? A chemical formula is composed of symbols of the elements that show the ratio of the atoms present in the compound, and it has two types. The first type is molecular formula. It shows the actual number or the real number of atoms in each element in the compound. Like for example, H2O2 or hydrogen peroxide. It shows that it has 2 hydrogen atoms and 2 oxygen atoms. For the second example, this is called glucose. It has 6 carbon atoms, 12 hydrogen atoms, and 6 oxygen atoms. The second type of chemical formula is empirical formula. This shows the simplest ratio of atoms in the compound, or basically empirical formula is the simplified term for molecular formula. Like for example, the simplified term of hydrogen peroxide is HO, and the simplified term for glucose is CH2O. And that's all!
What is inorganic compound? Inorganic compounds are chemical substances that do not contain carbon-hydrogen bonds, unlike organic compounds. They are typically found in minerals, rocks, and water, playing crucial roles in various natural processes.
Okay, hello. I want to share my knowledge about ionic and covalent compounds. So let's get straight to the point. Ionic compounds are composed of one metal and one nonmetal, while covalent or molecular compounds are composed of two nonmetals. When you name, before that, we should talk about the crisscross method. The crisscross method is a way to find a correct and accurate formula for the ionic compounds. Since we have here an example of crisscross method. This is how we use it. We have zinc and oxygen. They both have a superscript of 2, a charge of 2, but one is negative and one is positive. So they should both cancel each other out. It would be considered balanced already. Therefore, we have zinc oxide with no more superscripts or charges. Superscripts, yes. Another is this. This formula is not balanced. We can switch their charges to balance it. So we put 3 there and put the negative here. So it would become aluminum chloride. Let's move on to naming ionic compounds. Some general rules of naming metal and non-metal binary compounds include cation is always listed before the anion. Cation and anion net charge ratio must be balanced or 0. The ratio is always expressed by the smallest whole number. The uncharged English name of the metal should be used. Naming the cation. If the cation is a fixed charge, it should be named after the element. Has more than one charge, it should be indicated by a Roman numeral suffix to the name of the element. For higher charges, we should use the suffix "ik". For lower charges, we should use the suffix "us". Naming the anion. The name of the anion includes only the English root, then you add "ide". Example, sulfate and "ide". It would become sulfide. Oxygen and "ide", it would become oxide. Steps to naming the metal and non-metal binary compounds include naming the metal first, unless it's it has a multiple charge, we use the Latin name and the suffix "ik" or "us." Otherwise, if it's just a fixed charge, we should write the full name of the metal. Then secondly, we name the non-metal. We use the root of the non-metals and add the suffix "ide," like oxide, the one we talked about. Thirdly, check for oxidation state if applicable. If there is more than one charge, if there is multiple charges, we should specify the oxidation state by using Roman numerals in parentheses. For example, we have magnesium and oxygen. If we combine them, it should become magnesium oxide, because we need to change the last part of the root name and then "ide." So oxygen, "ide," oxide. Next, we have barium, and sulfur. Sulfur becomes sulfide because "ide." Barium sulfide. We have iron with a charge of 3 and oxygen. Oxygen becomes oxide, and iron will become ferric because it has a higher charge, 3, the charge of 3. Practice. Try and answer this. Your answer should be sodium chloride. If you got the answer right. Sodium plus chlorine, which becomes chloride, will be sodium chloride. For this, keep answering. We have tin and oxygen. So it becomes stannous oxide because if we look at it, given that we did a crisscross method before this, the subscript of 2 should be with tin. So meaning tin actually has a charge of 2, which is still low. So we put us and it's flattening. Stannum and us. Stannous. Then oxygen and "ide," oxide. So it becomes stannous oxide. Next, we have molecular or covalent compounds. As I said before, molecular or covalent compounds are composed of 2 nonmetals. For naming molecular compounds, we have a naming strategy. We use prefixes, no charge balancing required, and we should just memorize the prefixes from 1 to 10, which is the Greek prefixes. This includes mono, di, tri, tetra, penta, hexa, hepta, octa, nona, and deca. The least electronegative element is written first, this is the rule, followed by the more electronegative element. The suffix "ide" is added to the stem of the name of the more electronegative atom. And then lastly, when naming compounds formed of 2 nonmetals, we use the Greek prefixes, the one I mentioned, mono, di, tri, blah, blah, blah. But if there is only one atom of the first non-metal in the compound, we do not use the prefix mono. An example includes diphosphorus and pentaoxide. First, we identify the subscripts, so we have 2 and 5. And then we use the prefixes that are correlated to their numbers. 2 for di, 5 for penta. So we should have diphosphorus pentoxide if we combine the prefixes and their element. More examples include carbon and oxygen. Since oxygen has a subscript of 2, it becomes dioxide, so carbon dioxide. Sulfur plus fluorine, which has a subscript of 6. So 6 is hexa, so it becomes sulfur hexafluoride. Practicing, answer this. It should be carbon dioxide. Carbon plus oxygen. Oxygen becomes dioxide because it has a subscript of 2. And that's it.
We are now going to talk about acids. Acid is a substance that can donate a proton, hydrogen ion, or accept an electron pair in reactions. How to name an acid? These are the steps. We need to first drop the word hydrogen and then add the prefix hydro to the onion root and change the suffix "ard" to "ike", followed by the word acid. To make it simple, we need to start with the hydro, and then we need to get the onion root, then change the "ide" to "ike", and then add the word acid. Like these examples, HCl or hydrogen chloride and HI, hydrogen iodide. To make this or to name this correctly, we need to add the prefix hydro, and then we need to get the anion root of chloride, which is chlor, and then change the IDE to IC, hydro. So it will turn into hydrochloric, and then we will add the word acids, hydrochloric acids. Then for hydrogen iodide, we need to add hydro, and then we need to get the anion root, which is iod, and then we need to change the IDE into ic. So hydroiodic, and then we need to add acids, hydroiodic acids. That's how you name an acids. These are the exercises that you can answer, but you need to pause me. These are the answers to the exercises: hydrobromic acid, hydrofluoric acid, hydrosulfuric acid. So now let's move on. How to write a chemical formula for acids? It has 2 steps. Identify charges and then balance the charges with crisscross method. So here we have an example of hydrochloric acids. So the charge of hydrogen is positive, and then the charge of chloride is negative, and then we will crisscross it. Then they will cancel out since they both has 1 charge. So it will be HCl or hydrochloric acids. These are the exercises. You need to pause this to answer. These are the answers for the exercises: H2SE, HN3, HCl. So now we're going to talk about bases. Bases are named using a specific system based on their ionic composition. The most common bases are ionic compounds that produce hydroxide ions when dissolved in water. To make it simple, bases starts with a cation or a positively charged ion, and it ends with a hydroxide ions or OH negative. And a base has a rule. The name of the cation plus hydroxide. As we can see here in the examples, NaOH is named sodium hydroxide, KOH is named potassium hydroxide, CaOH2 is calcium hydroxide, and GOH2 is magnesium hydroxide, and lastly, LiOH is named lithium hydroxide. As we can observe from these examples, it all started with a cation and it all ends with a hydroxide. So we have here some exercises that you can pause to answer. And these are the answers for the exercises: barium hydroxide, strontium hydroxide, and cesium hydroxide. How to write chemical formula for base? There are 2 steps. The first step is to identify charges and then balance the charges by crisscross method. So here we have an example, aluminum hydroxide. Aluminum has a positive 3 charge, and then OH or hydroxide has a negative charge. So when we crisscross this, the three positive charge of aluminum will become the subscript of OH. We also have here some exercises for you to answer, but you will need to pause me first. Then, these are the answers for these exercises: RbOH, ZnOH2, and LaOH3. That's all.
Hello guys, here we are going to discuss about oxide. What is oxide? Oxides are chemical compounds that contains at least one oxygen atom and one other element. They are formed by the reaction of oxygen with another element, often a metal. So there are two types of oxides. First, we have the oxyanion. Oxyanions, also known as oxoanions. They are polyatomic ions that contains oxygen atoms bonded to another element, typically a non-metal. These ions carry a negative charge due to the presence of extra electrons and are commonly found in various chemical compounds. Example, nitrate or NO3, and sulfate, which is SO4 Oxyanions has common prefixes and suffixes. We use "ite" or we add "ite" if it indicates a lower oxidation state of the central atom. We add "ate" if it indicates a higher oxidation state of the central atom. We add "hypo" if it indicates an even lower oxidation state than the "ite" form. And lastly, we add "per" indicates an even higher oxidation state than the "ate" form. So here we can see some example. We have the example as chlorine. First, we add hypochlorite. The next, we make it chloride or ITE. Next, we make it chlorate, ATE. And lastly, the highest charge or the highest central atom, which is perchlorate. Next type of oxides, we have oxyacid. Oxyacids are a type of acid that contains oxygen, hydrogen, and at least one other element. These acids have at least one hydrogen atom bonded to an oxygen atom, which can dissociate in water to release a proton, H+, and form an anion. Example, sulfuric acid. And we have nitric acid. We have the rules of oxyacid. First is the structure. Oxyacid have the general formula of HMXON, where X represents the central atom, usually a non-metal, but can be metal in its highest oxidation state. M and N are integers that vary depending on the central atom and its oxidation state. Hydrogen atoms are directly bonded to oxygen atoms, not the central atom. And oxygen atoms are also bonded to the central atom. Next rules is the naming convention. The names of oxyacids typically follow a systematic pattern based on the central atom and its oxidation state, just like the ik, us, hypo, and per. Then we have the acidity trends. The acidity of oxyacids is influenced by two key factors. First is the electronegativity of the central atoms. It is the higher electronegativity of the central atoms leads to a stronger pull on the electrons in the OH bond, making the hydrogen ion more readily released, thus increasing acidity. Next is the number of oxygen atoms. When increasing the number of oxygen atoms attached to the central atom enhances the inductive effect, pulling electron density away from the OH bond and increasing acidity. Lastly is the polyprotic nature. It is when some oxyacids can donate more than one hydrogen ion, making them polyprotic acids. The acidity of each successive protons decrease as a negative charge on the conjugate base decreases. Then we have the example. We can see here that we still use chlorine. Oxidation state is at +1, +1. It is called hypochlorous acid. The next one, +3, chlorous acid. Next one, +5, which is chloric acid. And last one, +7, which is perchloric acid. Now, let's have some exercises. I'll give you about 5 minutes to answer this. And you can answer there, and we'll just proceed and check if you are right. So here are the answer. For SO3 -2, it is sulfur, which has oxidation state of +4, which is called sulfite. By the way, this is for oxy and ion. Exercise for oxy and ion. Let's identify this oxy and ion. Okay? SO3 -2, which is sulfur with a +4. It is called sulfite. SO4, which is higher than SO3, which have the +6 oxidation, which is called sulfate. You can see that we just added ITE in the lower and ATE in the highest. Next one is the nitrogen, NO2, with the oxidation of +3, it equals to nitrite, which is the lowest. And then NO3 negative, which is +5, higher or higher than +3, which is called nitrate. Next exercise is for oxyacid. Let's identify oxyacid. So again, I'll give you 5 minutes to answer it. We'll just proceed. You can just pause the video if you want. So the answer are: first, we use sulfur with the oxidation of +4, which is sulfurous acid. Next is that we have H2SO4, which is higher than H2SO3 with the oxidation of +6, which is called sulfuric acid. Next, we have the nitrogen, which with the HNO2 with +3, it is called nitrous acid. And last one, HNO3 with a +5 higher than +3, which is nitric acid. I hope you learned something. Thank you, and let's proceed to another topic.
Balancing chemical equations. Balancing chemical equations is a fundamental skill in chemistry that ensures the law of conservation of mass is upheld. This law states that matter cannot be created or destroyed in a chemical reaction. Therefore, the number of atoms of each element must be the same on both sides of the equation. In a chemical reaction, Reactants are the initial substances that undergo a chemical change. They are typically listed on the left-hand side of the chemical equation and are separated by a plus sign. For example, in the chemical equation for the reaction between phosphorus pentoxide and water, here, phosphorus pentoxide and water are the reactants. On the other hand, products are the substances that are formed as a result of the chemical reaction. In the same chemical equation, here, the product, which is phosphoric acid, is identified where the arrow points, usually on the right-hand side of the equation. It is important to remember that reactants are always located on the left side of the equation, while products are on the right-hand side. This simple convention helps to clearly identify the substances involved in the chemical reaction. Okay. Next, coefficients play a crucial role in chemical equations, as they indicate the number of molecules or atoms involved in a reaction. For instance, in the chemical equation here, the number 2 is placed before the reactant hydrogen and the product water are the coefficients. Those are the coefficients. So it is important to note that coefficients are placed before the elements or compounds in the equation. To balance a chemical equation, the first step is to write the unbalanced equation and identify the reactants and products, and then write their correct formulas. Once we have the unbalanced equation, the next step is to count the atoms of each element. To count the atoms, we look at the subscripts of the elements or compounds. If there are no visible subscripts, it is understood as 1. For example, here in iron, it has no subscript, so it is understandable as 1, or it is understood as 1. And oxygen has 2 atoms based on the subscript. In the products, iron has 2 atoms and oxygen has 3. Clearly, the equation is unbalanced. To balance it, we start by addressing the imbalance in the first of atoms of each element. First, we multiply the iron in the reactants by 2. Let's multiply it by 2 here. Then, this results in 2 atoms of iron, because we will multiply 1 times 2 and it will become 2. Okay. However, the number of oxygen atoms is still not balanced, with 2 atoms on the left side and 3 atoms on the right side. To balance the oxygen atoms, we multiply the oxygen in the reactants by 3, resulting in 6 atoms. Although this balances the oxygen atoms on the left side, the oxygen atoms on the right side are now doubled to the multiplication of the entire compound. Okay. To correct this, we then multiply the iron on the left side by 2, resulting in 4 atoms. Now, the number of iron is not balanced.
na siya balanced because the other side here is 2 and this is 2. No, this is 4. So let's us we will adjust the multiplier from 2 to 4. After this adjustment, the equation is finally balanced. So we then copy the multipliers, this, and this. Then copy the multipliers and paste them before the elements or compounds to complete the balanced chemical equation. So these are the coefficients now. Okay. In the balancing process, we need to ensure that the number of atoms of each element is the same on both sides of the chemical equation. Let's go through the steps to balance the given chemical equation. First, multiply the coefficient by 4 by the subscript of iron, which is 1. This gives us 4. It's correct. Then, let's multiply the coefficient 3 by the subscript of oxygen, which is 2, resulting in 6, and that is correct. So, finally, let's multiply the compound's coefficient, which is 2, by each element's subscript. So, 2 times the subscript of iron, 2, equals 2, 4, and that is correct. Then, 2 times the subscript of oxygen, which is 3, equals to 6. And this ensures that the given chemical equation is now correctly balanced. So, let's balance this equation. The reaction of hydrogen with oxygen to produce water. We need to ensure that the number of atoms of each element is the same on both sides of the equation. Starting with the reactants on the left side, we see that there are 2 hydrogen atoms and 2 oxygen atoms. However, on the right side, there are 2 hydrogen atoms and only 1 oxygen atom. Since hydrogen atoms are already balanced, we move on to balancing the oxygen atoms. To do this, we multiply the coefficient of oxygen, which is 1, by 2 to get 2. Thus, the equation becomes hydrogen reacts with oxygen and produces 2 water. Okay, next, since here madadamay din yung hydrogen, let's also put here a multiplier 2 because it will also be multiplied by 2 as it is as 1 with oxygen. So 2 times 2, that will be 4. So the hydrogen now is not balanced. So let's make it balanced. Then let's multiply the left side rather by 2 to make it 4. And now it is now balanced. Okay. So to verify if the equation is balanced, we check the total number of atoms on each side. On the left side, we have 2 times the subscript of H, which is 2, resulting in 4 hydrogen atoms here. Then, then oxygen as is 2 because there are no coefficients. It is already understood as 1. On the right side here, we also have 4 hydrogen atoms because there is a coefficient 2. So 2 times the subscript of hydrogen 2 is equal to 4. That's why we got 4. And 2 times the subscript of oxygen, which is 1, is equals to 2. So, as a result of the balance equation for skip to please. Okay. So this is now our final answer, the final balance equation, chemical equation. Okay, thank you for your attention to this chemistry problem.